Hello, welcome back to three-phase circuits. In this lesson, we're going to start the analysis of what we call the Wye-Delta circuit, where the delta is at the load end. And specifically what we're going to do is do the analysis with this configuration of the load to derive the equation for the current shift that we've been talking about all this time. You probably won't have to do this kind of thing on an exam, but it does, we're trying to learn where things come from here. So you just file it away and you really understand where that comes from, and so then it gives you confidence in solving your problems, even though you probably won't have to actually derive this equation on an exam. But it's an easy derivation, so let's go ahead and do it. Where we're trying to go, I should say the goal, what we're trying to do is we're trying to prove to ourselves that this line current, AA, is actually equal to the square root of 3 times I capital A B, which we can also call, in most books you'll actually see it written as the phase current, right, I phi, with a phase shift of minus plus 30 degrees. All right, that's what we want to prove to be true because we're going to use it for every problem from here on out. So what we really want to do is we want to write some equations and figure out what is the relationship between these two variables. I mean, we've written it down, we know what the answer is, but ultimately we want to explore how is the line current related to the phase current? How are these voltages related to one another? So toward that goal, the very first thing we want to do is we want to write down, we want to take in our analysis the phase current IAB as the reference of 0 degrees, okay? And because we're taking that as a reference, in other words, this current here, we're going to call it 0 degrees. All the other currents in the circuit will just be measured relative to it. So if we take it to be 0 degrees, that just means that IAB is going to have some magnitude associated with it. We'll call it the phase current magnitude. It could be 3 amps or whatever. And it has a phase angle of 0 degrees. We're just doing this by definition because we're taking it to be the reference. If we adjust our oscilloscope and our timing properly, we'll get the IAB current to be exactly a cosine at time t0. Everything else is measured relative to it. So since this is a balanced three-phase circuit, and this is what we call the A phase phase current, then if we take a positive phase sequence, let's talk about a positive phase sequence first. Positive phase sequence, right? Then that means IBC is going to be equal to what? It's going to be the same exact magnitude, but how is it going to be related to this? It's going to be negative 120 degrees shifted relative to it. And if you have a hard time remembering that, then you just go off to the side here. I guess I'll do it down here. This is going to be the A phase of whatever quantity we're talking about. This will be the B phase of whatever quantity we're talking about. And this will be the C phase of whatever quantity we're talking about. If it's a positive A, B, C sequence, then to go from here to here, it's a negative 120, and from here to here is a positive 120. Okay, so that's why for the B phase, we know we subtract 120 degrees because that's what it is to be a positive phase sequence. All right, now what would be that third phase? So CA is the third phase. You need to kind of get used to how these things are labeled. It's AB, that's the A phase, BC, that's the C phase, C has to go somewhere, back to A, that's what we call the C phase. It's going to be the exact same magnitude for a balanced three-phase circuit. What is going to be the phase angle relative to this? We're adding 120 degrees per our diagram here. So these are the three-phase currents. We can write them down without any calculation because we know that it's a balanced three-phase circuit. Whatever this circuit is connected to, because it's balanced, that means that the magnitude of all three phases of these currents are going to be exactly the same. And if we take this one to be 0, again, if it's a balanced three-phase circuit, then they're going to all be separated by 120 degrees. Minus and plus because it's a positive phase sequence. If we were to redo this analysis for a negative phase sequence, the only thing that would be different is this would be positive and this would be negative because the B and C would be flipped around here. But for now, let's just keep it simple and say positive phase sequence only. These are going to be our phase currents that are circulating around this little triangle region inside the triangle. But these are different currents than the line currents which are coming in and feeding them from the transmission lines. Obviously they're different, that's why we're deriving this conversion relation to begin with. So how do we go from understanding what these currents kind of look like to figuring out what these currents, the line currents, look like? What we're going to do is we're going to go to this node up here. This is a node, right? Every place in a circuit, every node in a circuit obeys Kirchhoff's laws, always, right? So we're going to write a Kirchhoff current law at the A node.